This is Mr. Potter. What we're going to be talking about today is the packets that we've mentioned so far as data is traveled across the internet, as well as the protocols that we've set up to make sure that packets get sent to their destination in a reliable manner. Well, as reliable as we can, given the state of the internet where things can become delayed or even lost in transit. How do we actually make that reliable so that we can use the internet for commerce or for any other type of data practical applications? So I want to go back to the idea of the IP packet. Remember, IP stands for the Internet Protocol, and there are several things that are part of an IP packet. The first thing you're going to see is the version number. And we talked briefly about how we have IPv4, which is a 32-bit addressing system, and then we have the new one that's currently in progress, the IPv6, which is actually a 128-bit addressing system. So for most of the internet that we're going to see, our version number is just going to be the number 4. And of course, keep in mind that all of these values are being written in binary, so this is written as a 4-bit binary number because we don't anticipate having a version much larger than 15 in the current setup. We also are going to have some header length because we're going to have to know something about how long this whole header is. How big are we talking about the data that we're sending that talks about how we're sending this data? We have both a header length and a total length. And we'll get into more detail about these a little bit. We've also talked about the source and the destination. And when we talk about the source and the destination, these are where we're headed. So, if I'm going to 67.89.102.34, if I'm going to this source, but if this is where I'm starting at, but my destination is 76.54.32.109. These are the IP addresses that we've been talking about in the past few videos. These are going to be stored in the IP packet. Keep in mind that both of these are subject to change because we saw that our router will often change as we go from a protected network or to a unprotected network. There's also something called network address translation, or NAT. And because we're running short of these IPv4 addresses, you might have your IP address translated if you're part of a company, an internet service provider that doesn't have access to very many IP addresses for all of their customers. If they don't have enough for one address per customer, your address is going to get NAT translated. And that's not a problem because you can still receive stuff through that NAT translation to your original computer. We're also going to have something called time to live because these packets are going to be distributed on the internet. So I have my ISP is going to send it to the people that it knows, but each of these people are going to send it to the people that they know. Some of these are going to be close to my destination. Some of these are going to go spiraling out of control and not get closer to my destination, actually get farther away from my destination. So I need to make sure that if this packet has been in the network for too long, that it just dies. And so the idea is that I'm going to keep track of some number here, and then every time it gets transmitted, it's going to be changed by whatever server it's passing through. It's going to be deducted by 1, basically a countdown. Eventually it's going to get to 1, and as soon as it gets passed off to another 0, some server is going to say a 0, and it's just going to get rid of the packet because it's been in the system too long. It's probably useless, or it's probably reached its destination through another source, or maybe there is no path from the source to the destination. All of those situations may cause a packet to get lost in the transition. And then there's going to be some type of checksum. In other words, some number that's going to make sure that these numbers haven't been tampered with. You may recall in some of the other videos that we've seen situation where you could have some tampering with the data so that trying to get to a website on one address might actually lead you to a more surreptitious website on another address. This checksum should help prevent some of that. If this number doesn't match the data that's contained in the header, then it's basically a bad packet. And then finally, we have the actual data. Keep in mind that we are sending data across the internet. This data needs to be part of this. This whole packet is going to run about 64 kilobytes. So all of that we've done here, this is much less than 1 byte, which means our data can be quite a bit more. But also keep in mind that if it's a larger packet, it's going to take more time to transmit. So we often see these things much smaller, much closer to 1 kilobyte, or even less in the case of a situation where I'm not transmitting that much data. I'm just transmitting a request for a web page, or I'm just sending confirmation that, yes, this is the amount that I'm trying to spend on this commerce site. But IP is only one part of the solution. There's something else that we have to deal with called the transfer control protocol. The idea behind the transfer control protocol is, how do I actually get this data through the internet? The transfer control protocol was another protocol that was invented by Vint Cerf, who we talked about earlier. And it keeps track of several things. Notably, of course, it keeps track of our source, keeps track of our destination, and it also keeps track of the segment number. Because what's going to happen is I'm going to be sending these packets, and because of the nature of the internet, some of them are going to be faster than others. Some of them are going to get ahead, and the receiver is going to receive these packets possibly out of order. So if I say that this is segment 1 of 31, and then later on they receive segment 3 of 31, then they know that they've missed out on segment 2 of 31, and so they should be expecting that. We'll also see an acknowledgement number. And the idea is that because we're talking about control being passed and forth between two different computers communicating to each other, I could say that, hey, I'm sending packet 5 out of 31, and I received packets 2 out of 18 so far. So make sure the next time you start sending stuff to me, you send with packet number 3. Now, there's also going to be a window size. In other words, how big of a packet of data can I accept at one point? Because maybe my router is slower, or maybe I'm on a souped up internet and I can accept larger packets. And then, of course, this transfer control protocol also has the checksum. So if any of these values don't pan out, then we know that this is a bad packet. So again, this transfer control protocol, and combined with the internet protocol, really is the backbone of the internet as we have today. This allows us to transfer data across the internet where the order of the packets aren't important. What's more important to us is the reliability, to ensure that all the packets have gotten there and the other computer acknowledges that they've received the packets. In other words, we know that nothing has gotten lost along the way, because if anything was lost, we would not have gotten acknowledgement and we would have resent it. And so this idea of sending and acknowledging, or synchronous and acknowledgement, this is how things are done on the internet. So what's going to happen is I'm going to have my source, and I'm going to have my destination, and my source is going to send a request for something. It's going to send a synchronization. My destination is going to send an acknowledgement, and then it's also going to send a synchronization, because it's going to say, I got this, did you get this? And then you finally send a follow-up acknowledgement. And this is called a three-way handshake, where I've got a synchronization, and then remember, the packet we talked about can talk about both sending and acknowledging data. So we have a SYN-ACK packet actually coming back from our destination to our sender, and then our sender acknowledges the acknowledgement. So I send something, you say I received it, and I let you know that I received your receipt. So it seems very complicated, but it really is essential in order to make sure that packets that do get lost are resubmitted. And TCP has a way of recovering these lost packets. What happens is, the first time that I'm dealing with sending packets, I'm going to go ahead and send 1 packet. And then once I see that you've acknowledged that packet, the next time I'm going to send 2 packets. And if you're able to show that you acknowledge 2 packets, the next time I'm going to increase it to 3 packets. But if you ever acknowledge fewer packets than I send, the next time I'm just going to send 1 packet. And I'll ramp up the number of packets that I send as long as you're able to keep up the pace. As soon as you're not able to keep up the pace because of network congestion, because you're dealing with too many requests on the receiving end, or what have you, then I'm going to go ahead and slam down and say, wait a minute, something's wrong. We're not getting full connection. Let's start off slow again. And it's this idea that everything that I send is going to get acknowledged. However many times I send it, it's going to be acknowledged that many times. That really makes transfer control protocol and the internet protocol work wonders for us. This is a system that's been in place on the internet since the 1980s, and it's still working fine 30 years later. So, what you're going to do is you're going to go to our favorite website, studio.code.org, and you're going to try this out, this situation. So, you're going to go to code.org, you're going to go to View Course, and under day 5, the stage 5, you're going to pick the second option here. This is where we're actually going to be doing packets and making a reliable internet. So I've got an unreliable internet simulator. It's unreliable, which means that some things are going to be problems. So it says messages must be divided into packets which may contain at most 6 ASCII characters. That's a problem because we are limited in size by the way our internet is. The packets that we send can only be up to a certain size. Otherwise, larger packets have a tendency to get lost because the server or the routers or the other computers along the way just can't deal with that many at that size. So we're going to have to make sure that we take care of these packets at most 6 ASCII characters long. We should send a message that contains at least 10 packets. Keep in mind that they may not arrive in the order, but we do have to acknowledge them. So as we go through here, it says the sender and receiver must be confident the full message was transmitted and reconstructed. And it must be at least 60 characters long, so your teacher's going to give you some message that you're going to have to send. Now, if you've ever played the game Telephone, where you have to whisper in someone's ear and then it gets passed around the room and you have to see how effective, this is the opposite of that. Because it's not important to have the secrecy to this. Keep in mind that our routers let everything know. We can look at the logs and see what happens. But we need to make sure that our data gets sent correctly and that our data gets acknowledged. So we're going to jump over here and just kind of show what's going on. Let me go ahead and erase this stuff. But we're going to go ahead and take a look at this. So we've got several routers set up. I'm not connected to anything, but the idea is that I can join one of these. And if I try and send a message, notice that if I try and send a message, if I do hello world, I can try and send it, but this message is going to be rejected because it's more than 6 letters long. And I'll actually see that in the logs. If I go over to my router and take a look at the log browser, I'll see that that message has been rejected. I'm limited to 6 characters here. And I'm limited to 6 characters, and these characters include my acknowledgement. Notice I've got 96 out of 64 bits down here in the lower right corner. So I'm going to have to figure out a way to send a message that's at least 60 characters long and receive acknowledgement from my destination. That's going to be what you're going to be working on today in class. So once again, this is Mr. Potter. Thank you for watching. Have a great day.